Hi, my name is Amelia, and I'm one of the graduate research assistants here at Mesmer Research Group. Thanks so much for tuning in. This week on the MRG Guest Speaker Series, we have Assistant Professor Dr. Paul Grogan tuning in from Stevens Institute of Technology. He'll be discussing robust collaborative space systems, design theory, and methods. We really hope you enjoy, and please don't forget to subscribe for more videos like this one.
Terrific. Thank you, Amelia. Really excited to share some of the updates on the work in my research group. So this work, of course, is not just my own work. I'll be presenting on behalf of my students, Ambrosio Valencia Romero, Jordan Stern, and Alkim Avsar are my three PhD students who directly contributed to this work. And I'm very excited to take you along the journey of how we've been thinking about robust collaborative design with specific applications to space systems. Just a preliminary, what really motivates me for the overarching framework for my work is to contribute to the Earth Science Decadal Survey, which was released a couple of years ago as a strategy document for aligning space system design to support Earth science mission objectives. So there are a huge number of scientific objectives that are very important for our society. And this document lists 6 specific areas as most important objectives, including studying water and energy cycles, ecosystem change, weather and air quality forecasts, so climate and societal response to climate change, sea level rise, and also geological hazards and disasters. Beyond these most important scientific objectives, though, this decadal survey also outlines some approaches that should be considered for how to achieve these scientific objectives through remote observation in space. And these include exploring innovative observing methodologies, leveraging external resources and partnerships beyond just the US government agencies, and also leveraging external technology trends. Space is a really exciting domain to be working in right now, and these strategy elements emphasize a new direction to be taken for future Earth observing missions. So just a quick snapshot of what Earth observation looks like currently. There is a large set of satellites, both traditional monolithic satellites, but also new classes of distributed satellite constellations that are being leveraged to improve our ability to observe activities down here on Earth more frequently and with higher resolution. However, the other big thing to highlight is that these missions are not just flown by US government agencies. So certainly NASA, NOAA, Department of Defense, USGS, these are some of the major players in Earth observing science missions. But increasingly, there's heavy reliance on international partners, including the European Space Agency and Japanese Space Agency, but also commercial players, including Maxar, Spire, Planet, and Capella Space. These are commercial firms that are flying their own satellites, producing data, and making that data available on the market. This is a huge opportunity to augment what has traditionally been a government-only program. And it's not just limited to commercial satellite operators. There are other commercial services, including satellite-based communication and ground services, including Amazon Web Services, Ground Station as a Service. These are huge opportunities to augment or improve upon, again, what has traditionally just been a government-run model. So the core of my research tries to understand when should these collaborative architectures be pursued? And by collaborative, I mean working across traditional organizational boundaries, either interagency, intergovernment, for example, international partners, or public and private collaboration for scientific objectives. Certainly, on one hand, the traditional mission architectures, which would be described as independent, have some real advantages. If there's one organization, one actor that controls all of the assets, they have almost supreme control over the scientific mission objectives that are achieved. However, by collaborating across organization boundaries, it may be possible to augment what you can achieve as one organization with resources that are leased or purchased or are shared across organization boundaries. So these collaborative architectures have a potential upside of improving efficiency of resources to achieve things like scientific observation of the Earth. However, collaborative architectures have a downside. If your partners, for example, drop out of your of a mission concept, you may actually be left with a less capable mission than what you would have otherwise been able to achieve at working as an independent actor. So in considering these collaborative architectures, there's an inherent trade-off between robustness if you pursue a more independent architecture to minimize your exposure to risk by essentially minimizing your connections with other organizations, and efficiency, where if you do leverage interactions across organization boundaries, you allow specialization of labor and also sharing of partial resources across organization boundaries, with, again, the potential downside of coordination failure and the losses that may result from that. So in addition to this top-level question of just asking when should collaborative architectures be pursued, we may also want to ask a follow-up question of how can collaborative architectures, such as the figure on the right, how can they be designed to be more robust to these strategic sources of uncertainty? And by strategic sources of uncertainty, I mean specifically the condition where a partner that you wanted to work with pulls out either through however means they pull out, either technical failure or business direction. It leaves you with a less capable system than what you had originally intended. So we see this as essentially a robust design problem. It's just that the uncertainty in the problem is a more social source of uncertainty. It's not an intrinsic environmental source of uncertainty. This is uncertainty in interactive relationships across organization boundaries. So in thinking about this problem, the way that we start is from a philosophical problem that goes back hundreds of years. It's best known today, or best described today, as the canonical stag hunt game, which is a classic coordination game or social dilemma, which has been described. So in a stag hunt game, you can imagine two hunters walking through maybe the forests of medieval France, trying to decide what to go hunt for dinner tonight. And they're faced with two major options: either to go hunt stag, which is the prize winning meal, or to go hunt hare or rabbit as a more boring type of hunt for dinner tonight. The trick is that to hunt a stag, both of the hunters have to coordinate, and they're both necessary to take down this very large animal. However, if they alternatively choose to go hare hunting, they can do it independently. They don't need both hunters to coordinate on hunting hare to be successful. So this poses a dilemma because a hare hunting strategy, it serves the place to be a more independent case. It's very similar to the independent mission architectures as are traditional, where there's maybe a modest payoff, a modest amount of food that you earn from the hunt, but it's pretty much guaranteed. You have very little risk, very little uncertainty in acquiring these rabbits for dinner tonight. On the other hand, a stag hunting strategy is a more collaborative strategy where you have to work with your hunter. And there's a potential upside there of successfully hunting a stag with your partner. However, it's uncertain, where if your partner backs off or experiences a coordination failure, then you may be left trying to hunt stag on your own, and you essentially don't have enough resources to achieve that individually, so you may go home hungry. So just to put some numbers on these four cases, you can see this matrix in the lower right-hand corner. So 2 indicates the amount of food or the amount of value that you get from a hare hunt if your partner also pursues a hare hunt. You get 3 units of food if you pursue a hare hunt and your partner chooses to go hunting stag. This is almost reflective of having more opportunity, right, to go hunt hare if you're doing it individually. So there may even be an upside for your partner to defect to go stag hunting, for you to go hare hunting. And in the bottom row, if you choose to go stag hunting, but your partner chooses to hunt hare, you go home hungry, so you essentially don't have enough resources to take down the stag yourself. And in the best case scenario, if you choose to hunt stag and your partner chooses to hunt stag, then you both go home with 4 units of food. This is kind of the best case scenario. So to think critically about what strategy would you choose if you were placed in this position, I want to have a little bit of audience participation. So I have a web-based activity where we can actually participate in hunting stag or hunting hare. So I'd like everyone to pull up a browser, pull up your phone, whatever the easiest way to get on the internet is, and go ahead and navigate to a website that I have set up for today. I'll post it in chat. The website is at hunt.code-lab.org, hunt.code-lab.org. And here you can sign into the website. You can choose any username you like. It doesn't even have to be your real name, but it's best if you do use your own real name for your username. And the passcode to enter today is Attila. It's Stephen's mascot, Attila the Duck, A-T-T-I-L-A. So go ahead and log in, and you'll be presented with a user interface where you can select either hare hunting strategy or a stag hunting strategy. And you can see in terms of the payoffs, if you choose a hare hunting strategy, you're either going to earn 2 or 3 points. And if you choose a stag hunting strategy, you're either going to be earning 4 or 0 points. The way that we're going to have this set up is you're initially going to be paired with a random computer AI. And the computer AI is going to randomly choose between hare hunting strategy and stag hunting strategy with a 50-50 probability. So go ahead and choose the strategy that you want to select. I'm going to pull up my administrative interface. We're going to play, I'm going to play a series of about 10 rounds, and I'm going to show the results of the decisions that everyone in the room has made as we're going through this. So let me set up the game and let's score a first round. So in this first round, we see that of the individuals in our room, we had 6 people choose the hare hunting strategy and only 2 chose the stag hunting strategy. And in terms of outcomes, the most common outcome actually was you choosing hare and your partner choosing stag was the most common outcome with being paired with a random player. So let me go ahead and score a few more. I'm going to click this a total of 10 times. If you want to choose your strategy, go ahead. So here's game number 2, game number 3, game number 4, game number 5, game number 6, game number 7, game number 8, game number 9, and game number 10. So let's take a look at the scoreboard to see how evolutionarily fit we are as hunters. And we have AK Falcon was at the top of the leaderboard. I don't know if AK Falcon, if you want to either unmute yourself and maybe just give a quick description about your strategy that you followed, or you could type it in chat as well if you'd like.
I just selected, I went back and forth, to be honest, between hare and stag.
Awesome. And we did see over the different stages, we started with relatively low stag hunting, and we did see an increase in stag hunting over time. So think carefully, think about the rationale that you have for making making these types of strategic decisions, and let me adjust this game a little bit. So instead of having this default game that we were playing, let's make stag hunting a little bit more dangerous. So by dangerous, what I'm going to do is I'm going to change the downside payoff to a negative value. So rather than earning 0 points in a failed stag hunt, now you'll earn -8. It'll actually decrease your point total. And this could be representative, for example, of getting hurt in a stag hunt that you have to go alone at. So with this change, you can go ahead and make changes to your strategies. And we're going to play 5 more rounds. So go ahead and choose your strategies that you'd like. And I'm going to score 5 more rounds of this game. So ready? Here's game number 1, game number 2, game number 3, game number 4, and game number 5. So if we look at the scoreboard, we did have a change in lead runner. Casey is now in first. Think to yourself, how did this change in payoff, this added downside risk, change your calculus about how do you value stag hunting versus hare hunting? And as you're thinking about that, let me make one more change to the game. Rather than having a painful loss of a failed stag hunt, let's make the stag a really big stag. So instead of having 4 points of benefit from a successful stag hunt, let's make it 8 points of benefit from a successful stag hunt. So think about how that changes your strategy. We're going to play 5 more rounds of the stag hunt. So go ahead, update your decisions. So here's game number 1, game number 2, game number 3, game number 4, and game number 5. So we saw pretty dramatic shifts in terms of strategy. And of course, just by inspecting the deltas, from game to game, those might be expected. But it's interesting to think about what actually drives the decision-making for choosing stag hunting strategies versus hare hunting strategies. And let's just do one more example, one more case. So I'm going to put back to the default game. 4 points for a successful stag hunt, 0 points for a failed stag hunt. But now, instead of being paired with a random robot, I'm going to pair you with someone else in the room. When I click setup, you're going to see the name of your partner on the call. If we have an odd number of people, you may be paired still with a random robot. And let's play 5 more rounds of the stag hunt now that you know that you're no longer paired with a robot that chooses stag 50% of the time. We are being paired with a live human being somewhere in the world. So we'll play 5 more rounds. Here's 1, 2, 3, 4, and 5. So we did see more strong adoption of stag hunting strategy in this case. Of course, there are all sorts of complex factors to consider, like history effects and visualization of seeing the strategy selected by everyone in the room each round, and also pursuit of trying to get to the top of a leaderboard. But nonetheless, this mental framing helps us understand the same types of decision that comes into choosing between a collaborative space systems architecture and an independent architecture. So let's dig into this in a little bit more detail. So a stag hunt in game, game theory is the set of economics that would be used to think about these interactive decision-making problems between more than one intelligent actor. The way that we'd represent the stag hunt in the most simple representation is called a normal form matrix. This normal form matrix, or bimatrix in some cases, shows what are the payoff values that the 2 actors would receive in each of the different strategic alternatives that are possible. So here the black player and the red player both choose between hare hunting strategies and stag hunting strategies. And we can see the red and black payoffs in each cell, which correspond to the amount of food that each of these 2 players would receive. So in this game, through the lens of game theory, there are actually 2 stable solutions that are called Nash equilibria. These are strategies where neither actor individually has any incentive to deviate or change their strategy based on knowledge, based on a fixed decision of their partner. So these 2 Nash equilibria are the hare-hare strategy and the stag-stag strategy. Of course, the stag-stag strategy has the highest payoffs. This in literature is called the payoff dominant strategy, or the payoff dominant equilibrium. But the hare-hare strategy is not to be disregarded either. It's also a Nash equilibrium, meaning that if both players are focused on a hare hunting strategy, neither has incentive to deviate to the stag, because they would essentially lose out on value. And in literature, this strategy is sometimes called risk dominant. And in this particular case, the hare hunting strategy is indeed risk dominant. And theory and equilibrium selection theory actually says that the risk dominant strategy is the strategy that should be selected by rational decision-making actors under certain circumstances, even if there's any sort of grain of doubt that your partner is going to follow through with the more collaborative, the higher payoff option. So this risk dominant option, which is the hare hunting strategy here, even though it's economically inefficient, this is actually the stable solution that actors would gravitate towards over long time durations. And we did see actually pretty prevalent hare hunting strategy, at least in the first round of our friendly experiment. So let me give you a little bit of intuition on risk dominance and why it might be a preferable option to choose. And to do that, I'm going to take a step away from game theory and just look at this problem through expected value maximization. So on the x-axis here, I'm showing that the probability that your partner chooses stag ranging between 0 and 1. So for 1 on the left-hand side, your partner always chooses hare. For 1 on the right-hand side, your partner always chooses stag. So here we can calculate the expected payoff of our different strategies that we have available to us, hare and stag. So hare, for example, ranges between an expected payoff of 2 if our partner always chooses to hunt hare, and 3 if our partner always chooses to hunt stag. On the other hand, the stag hunting strategy has an expected value that ranges between 0 if our partner always chooses hare and 4 if our partner always chooses to hunt stag. The really interesting thing about these expected value lines is that they intersect. What that means is that for a certain region of this probability space, the hare hunting strategy actually maximizes your expected value. For anything left of this intersection point, if we assess that's the probability of collaboration for our partner, we should rationally choose the hare hunting strategy. On the other hand, if we have a probability of collaboration that's higher than this crossover point, then we should choose the stag hunting strategy because that maximizes our expected value. So this crossover point is actually a very important point in equilibrium selection theory. I've notated it here as the variable u on the x-axis. You can think of this as the threshold probability of collaboration required to pursue the payoff dominant equilibrium, the stag hunting strategy. And in this particular problem, u, which is also called the normalized deviation loss, has a value of 2/3. So if you think that your partner has a better than 2/3 chance of selecting the stag hunting strategy, you should also select the stag hunting strategy. Otherwise, you should select the hare hunting strategy. The challenge, of course, is that your partner can also perform the same type of analysis. So this expected value problem itself is insufficient to solve this equilibrium selection problem. Fortunately, however, Selton, in his 1995 article, around the time when he received the Nobel Prize in economics for his work on game theory, proposed a metric that analyzes a game from a global perspective. He calls it the risk dominance measure. If this risk dominance measure R is bigger than 0, then hare is the risk dominant strategy, the risk dominant equilibrium, and should be pursued by rational actors. Alternatively, if R is less than 0, then the stag is the risk dominant equilibrium, and it should be pursued as the solution concept. What's more important, though, is that the magnitude of R indicates the strength of the conclusions that can be drawn. So if R is pretty close to 0, then it's hard to say whether hare hunting or stag hunting is truly better. It depends more on contextual differences. However, if R is very large, then we have much stronger conclusions we can draw about whether hare hunting or stag hunting is more desirable. So R is formulated simply as the logit of the normalized deviation loss U. Selton has like a 40-page paper of proofs and axioms that give much more detail about why this is a desirable form, but I'll leave that for reading after our session today. The big idea is it transforms the normalized deviation loss U into this value R. For positive R, hare is risk dominant, and for negative R, stag is risk dominant. And for this very simple class of problems that we've looked at so far, it equates to if U is bigger than 50%, hare is risk dominant, and if U is smaller than 50%, stag is risk dominant. So this first game that we looked at with four units of food for a successful stag hunt, this has a risk dominance function of around 0.7. So it's slightly tilted towards hare being the risk dominant option. So it actually makes sense for many of you who selected the hare hunting strategy in our first round. That's actually a preferred strategy under the perspective of risk dominance. There are, of course, extensions of risk dominance to more complex problems. If you have more than 2 players or if you have asymmetric cases, there are more elaborate forms that can be used as well. So if we wanted to compare a couple of these games that we looked at, this first game, as I mentioned, has a risk dominant score of around 0.7. That means that the hare hunting strategy is slightly preferred. The third game that we looked at, where we're hunting the really big stag, this actually has a negative risk dominant score. So that upside potential with having a really large payoff from a successful stag hunt, that pushes the equilibrium, the risk dominant equilibrium, towards the stag hunting equilibrium. And that actually is the preferred option in this game. And the second game that we played, where there was this risk of injury from an unsuccessful stag hunt, this has a much higher risk dominance score. So this should push the strategy selection closer to the hare hunting strategy. So the key component about risk dominance is it reduces an entire game, a normal form game, to one number. One number describes the dynamics of the strategies that could be played by intelligent players that are thinking of a very long time horizon. This formulation of risk dominance, though, it fits into a bigger picture of literature on strategy dynamics, especially in coordination dilemmas or coordination games. So I just want to draw one connection. So for games, you can transform the payoff matrix to have the hare hunting strategy have payoff 0, the stag hunting strategy have payoff 1, and then simply vary the payoffs for the red player and the black player in these off-diagonal cases. And here I've represented those payoffs just as S and T. If we plot, if we consider different values of S and T, these are two technical terms in game theory literature, the temptation to defect and the sucker's payoff. We can actually see many different types of strategic dynamics that emerge for different values of S and T. So the region that we were looking at for the stag hunt game actually falls in the bistability region, where the risk dominance score separates the stag normative strategy from the hare normative strategy. However, there are other regions as well that are interesting, including the defection region, which is where the classic prisoner's dilemma problem exists, and also the coexistence region, where the classic hawk, dove, or chicken games exist. So within this representation, a couple of the games we've looked at so far, the starting game with a risk dominant score of 0.7 appeared in the hare hunting normative region, and this problem with the dangerous stag hunt is pushed up into the stag hunting dominant region. So one of the criticisms you could have at this point is that this theory is pretty highly simplified, and how would it scale up for things that are not single shot 2-player games? And part of the work that we've done in my group is to look at multi-agent simulations of networks of agents that, instead of playing one stag hunt game with each other, actually play a series of stag hunt games with each other and have a reinforcement learning rule to identify what is the best performing strategy to maximize your individual payoff over a long time horizon. And we looked at many different types of network topologies, ranging from lattices to random graphs. And in all of these cases, if we look at stag hunting games that span the range of S and T, in all of these cases, we do see clear delineation around the value of R equals 0. So R equals 0 separates the games where the majority of actors converge to hare hunting strategies to the cases where the majority of the actors converge to stag hunting strategies. Now, one of the interesting features is that the delineation is clearest for certain networks, like the von Neumann lattice, where the R equals 0 line is a very strict differentiator between hare hunting and stag hunting strategies. Whereas for other graphs, other more complex topologies like random graphs, there is a gradient where games that have a risk dominance score close to 0, it could go either way, depending on the initial conditions of the graph. So the main conclusions from this is that the risk dominance score, the main conclusions from this work is that when to pursue a collaborative system, it looks like it really can be modeled as an equilibrium selection problem. Even though the stag hunting game is a highly simplified representation, it has a lot of the same components that we're looking at for upside potential and downside risk of collaborative options. And we also can see that risk dominance is an important solution concept. The sign of R indicates which of the two strategies, hare or stag hunting, independent or collaborative, seem to be preferred under idealized conditions. What's more important is that the magnitude of R indicates the strength of stability of these conclusions under various perturbations, like differences in network topology, learning rule, time horizon, all sorts of things like that. So the question that remains, though, is can we design the payoffs through engineering design to help lead to more desirable outcomes? Is there anything we can do to help increase these values of risk dominance to higher levels, giving us more likely, more probable successful collaborations under these collaborative architectures? So to do that, the work in my group has introduced what we call a bi-level model of design, where yes, at the top level, we still have strategies that agents select, but these strategies are from a very limited strategy space. We still essentially preserve a hare hunting strategy and a stag hunting strategy. And these are analogous to pursuing an independent architecture, for example, for your space system, or a collaborative architecture for your space system. The additional lower level layer, though, is we allow agents to customize how they implement their strategy. And in the stag hunting analogy, this is like choosing your weapon that you're going to go hunt a stag or a hare with. And you may have a large set of options for weapons to choose among, and the weapon that you choose directly impacts the value that you may get under the different strategic contexts. So in transforming this game to a bi-level representation, we can think of not just having two strategies, but two strategies and four maybe design alternatives to implement each strategy with. Some of these design alternatives are really good in certain contexts. For example, the dog design alternative gives us high value in hare hunting contexts, whereas other strategies like the addle-addle gives us high value in a successful stag hunt. So if we choose particular designs for our actors and then reconstitute or recreate the normal form games, we can then analyze the effect of lower level design decisions on upper level strategy dynamics. So for example, if you choose the dog to go hare hunting and the addle-addle to go stag hunting, you're left with this first game that we started our discussion with. However, if you choose dog to also go stag hunting, it's probably not a good idea because this dog doesn't give any value for a stag hunt. Alternatively, though, if you chose a club to go stag hunting, it does give you some upside potential, but it's not quite as good as the addle-addle was in the first place. And this is reflected specifically through a high risk dominance score. On the other hand, there may be some other design alternatives like the bow, which still gives us a reasonably high level of value under successful stag hunts, but also defends against coordination failure by giving us some value under an unsuccessful stag hunt. And this bow option actually has a higher risk dominance score, a lower risk dominance score. It makes it more preferable to pursue collaborative options than where we started. So if you think of a large trade space of lower level design decisions, you could hypothesize that they could be distributed such as this, where we could show the risk dominance measure on the x-axis and the upside payoff for an actor on the y-axis. So on this plot, we could imagine finding a set of payoff risk dominant Pareto efficient alternatives. These are the set of the designs that either maximize the upside potential or minimize risk dominance for a given player. And we can imagine that these payoff efficient, this efficient frontier may include relatively risky options like choosing the addle-addle to hunt stag. It certainly doesn't include dominated solutions like choosing the club to hunt stag, but it may include what I call risk competitive or robust collaborative options like the bow that may not give you the best upside potential, but they do improve the collaborative dynamics of the problem by reducing essentially the probability of coordination failure. So to test this hypothesis in a little bit more detail, I want to introduce an application case to actually look at space systems. So we wanted to see, does a more realistic collaborative system design problem, can it still be modeled as a stag hunt game? Do we still get this stag hunt dynamic? Even under cases with asymmetry between players, having payoff values be computed by domain-specific models rather than just cartoon, sketch models, and considering a large combinatorial design space. And more specifically, we want to see, do these hypothesized risk competitive or robust collaborative designs exist? Do they give us new options that help us trade upside potential with downside risk? So for this application scenario, we considered two space actors. one that designs and operates a satellite communication system, one that operates an Earth observation system. If they pursue independent architectures, the satellite communication system earns revenue through a subscriber base. And the Earth observation system earns revenue by collecting imagery and then downlinking that imagery to a ground station with the shortest, at the shortest possible data latency time. If they pursue a collaborative architecture, there may be some upfront costs of having intersatellite links, for example. But under a collaborative architecture, the Earth observation system may be able to cross-link data soon after observation to the communication system for a fee, for a service-based fee. And the communication satellite system can downlink that data more rapidly to a ground station. So this is the value proposition for the upside of a collaborative architecture. So we've just in this problem, we've described the trade space of variables to be characteristic of a typical space systems trade space study. A number of design variables for the communication system with a goal of maximizing net present value from user subscriptions. The Earth observing system also has a number of design variables with an objective of maximizing net present value from completing imagery missions and downlinking data with low data latency. A lot of the details here are not described. I'm happy to refer you to the paper that we currently have in review on this. So to perform analysis for this application case study, we took a two-step analysis method. The first step was to unleash a genetic algorithm, a GA, for each of the system operators, the satellite communications operator and the Earth observing operator, to determine what is the design for each of those that independently maximizes their value, given their net present value objective function. So these two solutions are labeled as, you can think of it as the hare hunting option. If you know you're hunting hare and you think your partner's hunting hare as well, what design are you going to choose? What space system are you going to choose? Secondly, though, we also unleashed a genetic algorithm to find collaborative architectures that achieve three objectives. So certainly a collaborative architecture, we want to maximize the upside potential for both the Earth observing player and the satellite communications player, but we also want to minimize the risk dominance. If there's a low risk dominance score, that means it's favorable for both of the partners to pursue the collaborative option in the first place. So the results of these analyses show for the independent architectures, there was one architecture identified for both the Earth observing player and the satellite communication player that maximizes net present value. And under the collaborative architectures, there's actually a trade space of designs that does indeed follow this overall pattern that we've identified or hypothesized previously. Under the collaborative architectures, the satellite communications architectures are essentially unchanged, but there are a number of Earth observing architectures that have desirable properties. So certainly there's the most risky option, which is the highest payoff for the Earth observing player. That's actually if they have no individual ground stations, if they rely completely on their partner for downlinking data. That's a risky option, but it has the maximum upside potential for the Earth observing player. There are, in this case, two risk competitive alternatives. One risk competitive alternative has a slightly less ambitious deployment strategy for satellites, still relying heavily on the partner for downlinking data. And the less risky risk competitive option preserves the Earth observing satellites' independent ground station capability. So they do take advantage of cross-linking to the satellite communication player if it's available, but if there is a coordination failure in that case, they can still fall back on their original architecture of having 3 dedicated ground stations for downlinking. Now, I would say that these 3 architectures, choosing among them, of course, is not simple. If you have high reliance on your partner, if you think that your partner is reliable, then you may indeed want to pursue one of the higher upside potential. However, even if there's a grain of doubt about whether your partner is going to follow through on a collaborative venture, you should seriously consider this risk competitive or robust collaborative design, because it gives you a pathway to improve upon your independent architecture. This does have a higher net present value of around 475 compared to 347. It does have a benefit, but it doesn't have all of the risk that the most risky options have that carry along with it. So we argue that, yes, so first, this problem does indeed exist a stag hunt dynamic similar to the highly simplified games we've been talking about so far. And we've been able to identify that there do exist some robust collaborative solutions that should be considered by the players involved. So one of the main insights from this work, though, is that pursuing the maximized upside potential of collaboration, this is truly a fragile solution where these grains of doubt about your partner fulfilling a collaborative venture can push you to choose an independent architecture and potentially lose some of the upside benefits of a collaborative architecture in the first place. However, what we've found, or what we consider, is that even thinking about pursuing a robust collaborative design in the upfront stages can trigger a social reinforcing feedback loop that can make these more fragile designs achievable in the future. So the way that this works is if you look to collaboration to improve your expected value, start with the simplest possible case, a collaborative architecture that gives you some benefit to an independent architecture, but with very little downside risk. When you've established an increased, when you've established a higher expected value of collaboration, that makes it more likely that you yourself, as one of the actors in a game, will pursue a collaborative option. And through social interaction and through the lens of game theory, if you have a higher probability of collaboration, that influences in these stag hunt style games your partner to also have a higher probability of collaboration. And if your partner has a higher probability of collaboration, that directly influences your expected value of collaboration that you'd expect, because there's a higher chance it's going to be successful. This is really interesting. This is a positive reinforcing feedback loop. Once this feedback loop starts, you can strengthen the collaborative relationships across organizational boundaries and potentially in the future transition from a first collaborative architecture to a future collaborative architecture, which may have been too fragile to pursue as a first step. So what's essential for this, though, is that having higher subjective confidence in collaboration can help support these more fragile design concepts. And this plays a huge role for how we structure our systems engineering activities to essentially try to support or reinforce our subjective assessment of probability of collaboration, try to assure members of a system of systems that, that the resulting system of systems will be successful. So these conclusions actually provide theoretical and methodological support with other existing architecting principles and system of systems. For example, the seminal work of Mark Meyer. Identifying a stable intermediate form is very similar to pursuing one of these robust collaborative architectures. It's a first step towards pursuing your ultimate goals. And it also highlights the importance of identifying mechanisms to ensure cooperation. We didn't even touch here on all of the contracting mechanisms or cost sharing agreements that might be employed to help share the risk of coordination failures across different asymmetric parties. What's more, though, is that this approach, this way of thinking, gives us guidance for a new set of collaborative design methods. Essentially, we want to, throughout activities in systems engineering, we want to try to reduce the cost of collaboration. If we can reduce the downside risk of collaboration, it can start to trigger this positive reinforcing feedback loop that can lead us to more successful collaborative architectures in the future. And even considering in early design stages a robust design alternative can be one of these stable intermediate forms to hang our hats on for future work. And what I can't emphasize this enough, many of these factors are social factors. So if we want to influence the pursuit of collaborative architectures, we need to have open lines of communication across organization boundaries where actors can communicate their strategic intent and give reassurance through signaling that they are committed to pursuing collaborative options and they are interested in establishing stable intermediate forms as a first step to pursuing ultimate goals. So we're currently looking to implement some of these insights in an operational systems engineering activity. I'm a part of a large team within NASA's Earth Science Technology Office that are developing what we call the New Observing Strategies Testbed. This is a computational environment that seeks to further new observing concepts using system of systems across traditional organizational boundaries by prototyping and maturing core technology in a computational environment. Think of it like a benchtop prototype environment before deploying these systems to the real world. So this new observing strategies testbed as a computational platform seeks to validate new technologies that are necessary to realize distributed system-of-system concepts for Earth observing missions, and to help demonstrate these new operational concepts in a way that's lower cost and lower risk before an operational mission would naturally happen. And what's more, as this computational platform is bringing actors together, it helps to socialize new technologies, both with the technology community and with the science community, to start this positive reinforcing loop that collaborative architectures like distributed system of systems can be stable and can have stable intermediate forms to pursue the future vision for what we would like to see for Earth observing systems. So to summarize my talk, I hope I've convinced you that game theory provides the necessary foundation to understand strategic behavior, specifically in collaborative systems where there's more than one intelligent actor that's looking to pursue their individual objectives. I've explained how risk dominance can be drawn out of economic theory to be an informative measure to characterize dynamics in strategic problems. The most important thing is the magnitude of risk dominance helps describe the strategic stability. And if we can have, large magnitude problems that have large magnitudes of risk dominance, preferably in the negative scale, those are the ones that are more likely to be successful under collaborative architectures. What's more is through design, we can actually augment the risk dominance in these types of strategic problems by identifying and exploring a large trade space of lower level designs. We can try to find those designs that tailor the risk dominance score to the preferences and the dynamics of an individual set of actors. We've been prototyping these new trade space analysis methods that can use risk dominance as an additional criterion to help reveal robust design alternatives. And through my work on the new observing strategies testbed, we're developing social environments for exchanging these types of strategic intent among actors as a form of economic signaling to help indicate interest and pursuit of these collaborative architectures, which can provide much more efficient value for everyone in society. So with that, I would like to, of course, thank my sponsors of this research. This research is sponsored by NASA's Earth Science Technology Office, the National Science Foundation, the US Department of Defense, and most of the work that I presented today is the work of my students. Brosio Valencia Romero, Jordan Stern, and Alkeem Afsar have contributed significant components to this work. With that, I'll leave you with a few references to some of the source material, and I'd be happy to take questions. Thank you very much for your attention.
Awesome. Thank you so much, Dr. Grogan. That was very interesting. At this time, we will open the floor for any questions, if anyone has questions.
Yeah, I'll ask the first question. Hey, Paul. So I'll ask the question that all game theorists get asked from, you're looking at this from a normative side. What happens when we apply this in real design context and people make strategy choices that is not in their best interest, right? It's not even a dominant strategy. It's just kind of a rando strategy that they choose because they have some beliefs that might be driving them towards a different path.
That's a great question. Certainly, I'm of the belief that individuals tend to make decisions that they believe to be in their best interest. I don't know of any case when someone would not make a decision that they believe to be in their best interest. It depends on essentially what their utility function is. So all of the economic theory that goes behind risk dominance assumes that you have a utility function that's an accurate representation of each of the actors' preferences. So I was kind of careful. So in all the examples I described the payoffs as being values or as quantities of food, and that's not exactly accurate. There would be an additional layer on top of that, which would be a utility function to transform that raw resource quantity into a value of utils that that particular actor cares about. And certainly depending on how much you like venison or how hungry you are that day or your risk attitude, your utility function is going to differ from someone else's. Now, if you can characterize your risk, your utility function, you can apply all of the results of this work. Now, eliciting utility functions accurately, especially in multi-stakeholder environments, is certainly challenging to say the least. There has been a lot of research over the past 20 years, especially in the space systems domain, on that topic. It's an active area of work that we're pursuing, specifically on risk attitudes. We found that especially in the space domain, there's a very significant difference in risk attitudes between government agencies and commercial firms, and that drives their view of the stag hunt game to be very different from one another, and it gives actually rise to some pretty interesting results. So if anyone's able to attend the CSUN symposium in October, we should have a presentation on that topic at that point.
Great, and yes, we have multiple students and myself planning to attend CSUN. And a follow-on question there for this NASA testbed team or program that you're involved in. How are they going about eliciting preferences or establishing the utility functions?
Yeah, so the testbed environment, it is intended to perform some design of experiments analyses where but the design of experiments analyses are performed more from a traditional systems engineering perspective, where there is a mission objective function that is defined by a program manager, for example, and different members of organizations bring a capability, observing components, communications components that serve functions to achieve that mission objective. So the objective functions in the design of experiments that are considered are more traditional from systems engineering. It would be interesting to get to the point where we could elicit utility functions from different actors, but that's probably a pretty far, pretty distant objective. The near-term objectives are more qualitative. So the results of economic theory show us that communication is important, right, between strategic actors. So even if you have your own internal utility function, it is essential for you to be in communication with other potential members of your stag hunting game, so you can accurately update your prior beliefs about how they will behave. So the testbed serves more of those qualitative purposes to be an environment, a platform on which the strategic interactions can occur, not necessarily as an evaluation platform for measuring utility functions or finding the risk dominant minimizing design option. That would maybe in the future that will be the case, but it's more qualitative in the near term.
Awesome.
Yeah.
Looks like, oh, sorry, Chris. Looks like we have about time for one more question. So go ahead, Chris.
Okay, yeah. I was going to say there's, I mean, obviously with any sort of like simple game theory implementation here, there's going to be elements of real world decisions that aren't necessarily going to be represented here. But one thing that I think is potentially really relevant in terms of the like collaboration decisions that's going on in like stag hunt formulation is that in the real world, there's often an extra alternative. I think a lot of times in tech industries and aerospace, when you see, a company and there's another company who has something that they could use that could make their systems better if they worked with them, what happens a lot of times is the bigger company buys the smaller company, and now they're only one company, and they get the benefits of the other stuff, but without having to share, profits with another deal. And in a stag hunt, kind of the hunters don't have the option to absorb other hunters. So how does like that sort of play into how we analyze these collaboration decisions, given that there's there's more alternatives actually available to real companies here?
That is a really interesting question that I've never thought about before. So certainly the primary concept behind game theory is more than one independent, intelligent decision-making agent. The one of the main simplifications that we've advanced in this work is reducing to 2 strategies, right? Actually, 2 strategies. If you allow the upper level and the lower level layers of decision making, I think that 2 strategies are sufficient to cover a large range of options. But you're right that it doesn't cover all of the options. And if you're asking yourself, so the question I'm really asking in this work is when should we pursue a collaborative architecture? Maybe there's another question of when should we make an acquisition? Of course, you can't acquire a government agency. Well,
yet.
maybe through lobbying you can. I guess that's an open question.
Give it a couple more years.
But so there may be other questions of, when should I acquire my competitor? That I think that question may fall under one of the different dynamical domains. My intuition is that it may fall. You'd have to, I'd have to think about that more. That's a really good point. So I guess the big thing is to this work has all been, focused on one specific question to advance the main understanding of pursuing collaborative options. But you're right that there are always in the real world more options available, and I don't think that all of those options will ever be unified under one common mathematical framework. So it's important to have multiple perspectives on the problem, depending on what you're trying to emphasize. But that's a really good point. I'm going to note that down for some future work.
Cool. Thanks.
Awesome. It looks like we have time for one more question if there are any other questions. Nope. All right. Well, thank you again, Dr. Grogan. This was very interesting. And thanks everybody for joining. See you later.
Thank you very much for the invitation, and happy to follow up with anyone afterwards. This has been a pleasure. Thank you.
Thank you.
Thanks, Paul. Appreciate it.
We really hope you enjoyed this seminar. For future seminar information, please visit uah.edu/MRG. Also, be sure to check us out on LinkedIn to stay up to date with the latest MRG news. Thanks, and have a great rest of your day.